Hello, welcome back. In this section, we are covering modeling with exponential functions. Many of you guys might find this section of exponentials and logs interesting because we will be looking at several application problems where we use the exponential function to model certain behaviors that we see around us. Okay, so take notes. 4.6, modeling with exponential functions. Okay, so here we're dealing with exponential growth. And when we deal with exponential growth, oftentimes we are concerned about the amount of time something doubles. So, for example, suppose that I have some bacteria. Okay, and so I have this bacteria, and it starts off as just one, and then it starts to divide every hour. Okay, so after the first hour, it divides, and now I have two. Okay, and then after another hour, they divide, and so then now I have four, and then they divide, and I have one, two, three, four, and then I have eight, and then they divide, and then next hour I have 16. Okay, and they just keep doubling every hour. Okay, so here at this initial time, at time zero, we have just the one, but then after 1 hour, then we have two, and then after 2 hours, I have four. After 3 hours, I have eight, and after 4 hours, I have 16. So here we can see how this is growing exponentially, and we can see that here the bacteria population in this case. Bacteria population. We can see here that the bacteria population growth that is happening here could be modeled with this function f of t equals 2 to the t. So that when I plug in into this function, if I plug in 0 here, 2 to the 0 is 1. If I plug in 1 here, 2 to the first is 2. When I plug in 2 here, 2 squared is 4. If I plug in 3, if I plug in 4, if I plug in 5. So that here I can actually figure out, okay, well, how much bacteria will there be after, like, say, 24 hours? Okay, you can just use this function now to make that prediction. Okay, now suppose that the initial amount is not one. So this is kind of the most basic case, that your initial amount is one, and it doubles every 1 unit of time, whether it's 1 hour, 1 second, 1 day. Okay, so this is the most basic case of doubling. Okay, but oftentimes it's not the case that the initial amount is 1. Okay, so let's take a look at that case. So suppose the initial amount is let's say 10 is 10, not 1. Okay, so this is a case that we will look at, and we'll look at this sort of case in general, whether the initial amount is 10 or something else. Okay. But let's use 10 as a concrete example. Okay. Then the population, let's suppose we still have the same doubling time over here. It's every hour. Okay. So then over here, then the population, so the initial amount is 10 and then it doubles every hour, right? So 10, and then it doubles, so it becomes 20, and then it doubles and that becomes 40, and then 80, etc. Right? Okay, and so here we can see, oh, well, this is 10 times 2, and then you double, and you double, and you double, right? And so here we can see that this here behavior can be modeled as 10 times 2 to the t, right? And so that's what the function would be that models this particular situation where the initial amount is not 1 like over here, but your initial amount is 10. However, these two do have in common the fact that they both double every hour. Okay, so if they both double every hour, but this one starts off with 10 and this one starts off with 1, um, the only difference is that initial amount. And so here we can see, just by looking at this, that the function that would represent this situation would be f of t, which equals 10 times 2 to the t. Okay. Okay. Now, suppose that, okay, so we looked at this case. This is the most basic case. You start off with 1, and your doubling time is 1 unit of time, 1 hour in this case. And then we looked at, okay, well, what if the initial amount is different? Okay, over here, what if the doubling time is different? Okay, so we'll look at that case. All right, so suppose the doubling time is not every hour. Suppose it's every 3 hours instead of every 1 hour. Instead of every 1 hour. Okay. So it doubles every 3 hours. Every 3 hours is when you'll be multiplying by 2. Okay, so not every hour. Okay, so then this function can be modeled by this 2, because it's doubling. The initial amount is still 1. Okay, t divided by 3 is the exponent. Okay, and this makes sense because if it's doubling every 3 hours, that's when you want to multiply by 2, right? Every 3 hours, multiply by 2. 3 hours goes by, multiply by 2. Another 3 hours goes by, multiply by 2. Okay, so here, if you plug in 3, we see we get 2 to the first. And then when we get to the second, that happens at 6 hours. When you plug in 6 hours here, 6 divided by 3 is 2. And the next time you multiply by 2 is at 9 hours. And the next time, every 3 hours, you'll be multiplying by 2. Okay? All right. So in general, so over here, in general, exponential growth with doubling time we have this function n of t equals, so we saw here up above that if you have an initial amount that's something other than 1, then that initial amount got multiplied by all of those powers of 2. So we see here that this is your initial amount. So here in the general formula, we will put n0. Okay, that's your initial amount. And then we multiply that by 2, and how often depends on the doubling time. If it's every 1 unit of time, then it's 2 to the t, because then that first hour or first second or that first year or that first month, that is when we get our first multiplication by 2. Okay. But if it's not happening every 1 unit of time, so if it's not happening at every hour or every month or every one whatever unit of time that you're using, but it's happening every 3 hours, like this example over here. Okay, so then over here, it would be not t over 3. That would be true only if it's doubling every 3 hours. But if it's doubling every 4 hours or 5 hours or 6 hours, then we need to change this number here. Because if it's 3 hours, then we would need t to be cut in thirds. If it's every 5 hours, then we would need t to be cut in fifths. Okay, so this is our general formula for exponential growth to double. Okay, so let's write down what all of these variables mean. So n of t is your final amount. After a certain amount of time. Okay. N0, now looks like an H. Let me write that over. N0 is your initial amount. Okay, so like if you start off with 10 bacteria, then we would put a 10 there. And then T is your time. That one remains our variable. And then the A, this is the time it takes to double. Time it takes to double. So this is a really great function here when you're dealing with things that are growing exponentially, because if you are just simply collecting data, let's say you notice something growing exponentially, but you don't start collecting data from day one. So you just go ahead and start collecting data whenever you notice something and you're kind of curious. Well, then you just go ahead and start your experiment. And let's say you start with this initial amount and you're like, oh, I'm kind of curious. I want to know, I wonder if this is growing exponentially. And so then you start to collect your data, and let's say your initial amount is like 700. And then you just keep collecting your data and you wait to see how long does it take to reach 1400. Okay, and then how long does it take for 1400 to reach 2800? So you watch all of that. Okay, and then if it seems like there is a constant of when it is how long it takes to double, then you found A, and then your initial amount is what you started with, that 700. So then now you have a function. And so now you can make a prediction. Oh, okay, well, based on the data that you collected, your doubling time is this much. Your initial amount was 700. And so now you can make a prediction about, oh, wow, it's going to take this amount of time for it to reach 1 million. Okay, so this is a very powerful function here. Okay, so let's take a look at a few application problems that uses this. Okay, so let's take a look at this one. Under ideal conditions, a certain bacteria population doubles every 3 hours. Doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. Okay, so we're going to do several things with this situation. So the first thing we're going to do is find a model, like a function. Find a model for the bacteria population. After T hours. Okay, so since this is a doubling situation, then we can use this doubling. You can think of it as a formula, this doubling function right here, to represent this situation. Okay, in order to use this, we do need to know the initial amount, and we do need to know the time A that it takes to double. Okay, so we need the initial amount, and we need the time it takes to double. And I believe in this situation, we do have those two things. So initial amount, 1,000, and it takes every 3 hours it doubles. Okay, so this is what we know. We know that here, and I'll even highlight it. So we have it right here. Doubles every 3 hours. So we're going to use that. Okay, so we have that. And then we also have this 1,000 bacteria initially. Okay, so we're using all of those pieces of information. Okay, so we know A, the time it takes to double, is 3. And we know that the initial amount, N0, is 1,000. Okay, so if we know those two things, those are exactly the two things we need here to write this function. So we can find a model for this bacteria population. N of t equals our initial amount times 2 to the t over 3. Okay, we can use this. We can use this now to make predictions. Okay, well, how long will it take? If we have 1,000, how long will it take to reach 10,000? How long will it reach to reach 100,000? How long will it take to reach 1 million? Okay. All right. So let's do part B. How many bacteria? How many bacteria are in the colony after 15 hours. Okay, so we use our function to find n of 15, okay, when t equals 15 hours. So we plug in 15 for t, okay, and we get 1,000 times 2 to the 5th, 1,000 times 32. So we get 32,000. Okay, so after 15 hours, there are now 32,000 bacteria. Okay, and let's take a look at this one here. Letter C. After how many hours? So now we're going to be making predictions. After how many hours will the bacteria count reach 100,000? Okay, so after how many hours? So we're trying to solve for that time. How long is it going to take for it to actually reach 100,000? Okay, so let's have a look. All right, so again, we are going to use this formula, n of t equals n0 times 2 to the t over a, right? And we have a formula with actual numbers here. So we're going to use this one, n of t, which equals to initial amount is 1,000 times 2 to the t over 3. So this is the one we're using, right? Because we said that the initial amount is 1,000 and the time it takes to double is 3. Okay, so this question is asking us to solve for t. We're solving for time, and over here, we want to know how long will it take for this final amount to reach 100,000. So I'm going to go ahead and put 100,000 here in the final amount position. And I am going to solve for t. We all know how to solve for t now, right? Because we spent a lot of time in the previous chapter, or the previous sections, learning how to solve exponentials. Okay. All right, so divide both sides by 1,000. We get 100 equals 2 to the t over 3. I'm going to use log to solve for the exponential. So I'm going to take the log of both sides. And taking the log of both sides allows me to bring down the exponent t over 3. Okay. I'm also going to rewrite this 100 right over here. I notice that, okay, I'm using common log base 10, and I notice this is also a power of 10. You don't have to do this part. I like to do things by hand as much as possible before I use the calculator, so I'm going to do that. All right, and then I'm bringing down my exponent. Okay, and I'm going to solve for t now. I'm going to multiply. Well, over here, I'm going to go ahead and simplify this. You can use your calculator the whole time through. Like I said, I like to do as much of it by hand as much as possible before I turn to the calculator. So here, this is actually going to be 2. Okay, t over 3 times log 2. Okay, so now I'm going to multiply both sides by 3 to cancel it over there. And now I'm going to divide both sides by log 2. And when I punch that into my calculator, I get 19.93 hours. So this is how long it's going to take for your bacteria to reach 100,000. Okay, 100,000. Okay. It will take about almost 20 hours. So that's quite a bit. That's populating pretty quickly, this bacteria. Okay. All right. So, sorry, am I making you dizzy? Okay, so that's how we do this particular situation. Finding a model, we use that initial function, that this one over here. And again, like I said, so long as you know that initial amount and you know um, the time it takes for that thing to double, that's all you really need to create a function that allows you to make predictions, that allows you to find out how much is there after a certain amount of time. Okay, so again, so long as you know the initial amount and the time it takes to double. All right, so bacteria growth is not the only place where we use exponential functions to model it. Population growth is also one of them. So let's take a look at this next example where we look at rabbit population. Population growth in general is behaves exponentially. So let's take a look. All right, so a certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. Okay. All right. So, first question, what was the initial size of the rabbit population? Okay. All right. So, again, using our doubling function, n of t, which equals to initial amount times 2 to the t over a. So using this, let's see what we can get. All right, so we need to find the initial size. So that's n naught. Okay, so we are going to be solving for this. So the question is, what other pieces of information do we have? Okay, so all right, so we do know that The population, the current population is 4,100, and that occurred 8 months later. So we know time, we know t is 8. We know this final amount after 8 months is 4,100. Okay, so far I know we have 4,100 after 8 months. And then A, remember, A represents the time it takes to double. It's doubling every 3 months. So that would be 3. Okay. All right. So I have this much and I need to solve for n naught. Okay. So I can solve for n naught because it's the only variable here that's left. Okay. So I can divide both sides by 2 to the power 8 over 3. Okay. So if I do that, I end up solving for n naught. Okay. And punching that into the calculator, I actually get a nice round number, 645. Actually, I don't. It's roughly 645. Okay. This is nice because now that I have n naught and I know the doubling time is 3 months, now that I have these two pieces of information, now I have a full function where I can make predictions. Okay. So let's take a look at part B. Estimate the population one year after. 1 year after the rabbits were introduced. Okay, so we haven't written down our actual function yet, but now is a good time. So we now know that our function is going to be n naught, which is 645, times t to the times 2 to the t over 3. Okay, so we now know this. We have our function. Okay. All right, so now I can use it to figure out how much there were a year after they left the rabbits. So n of 1 equals 645 times 2 to the 1 over 3. And if I, sorry, this is in terms of months and not years. So this is 3 months. So this unit up here needs to be in terms of months as well. Okay, so that is 12 months make a year. Okay, and so I get 645 times 2 to the 4th. And when I punch this in, I get 10,320. Okay, 10,320. That's a lot of rabbits after 1 year. Okay, and let's just kind of sketch a graph. You're dealing with much bigger numbers now when you're dealing with these exponential growth. So sketch a graph of the rabbit population. All right, so let's go ahead and do that. I know two points. I know the initial amount. Let's scroll back up. So I know the initial amount was 645. Okay. So here's my table. And my final amount. Okay, so at T0, we had 645. And then we know that at how many? 12 months, I end up with 10,320. Okay. All right, so T0 equals 645, and I need to get to 10,000. So I'm going to go by 2,000s. 2,000, 2, 4, 6, 8, 10, 12. And you know what? I have enough room. I didn't have enough room in my paper before, but now I do. So I'm not going to go by twos, I'll go by 1,000s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is 1,000. This one here is 11,000. Okay, and let's go here. We have 0 to 12. So I don't feel like going by ones. Let's go 2, 4, 6, 8, 10, 12, 14. This is T. All right, 0, 645. So I have a point right around there. And then 12 and 10,000. So I have points right around there. And we can see we have this exponential graph. Okay. Okay. Let's take a look at relative growth rate. Okay, it's still exponential growth. And what we're looking at here is the relative growth rate. Relative growth rate. And so we have this formula, N of T, that's in terms of the E, in terms of E. And so here we have E to the RT. Okay, so we have this. We have this formula here, which is slightly different from the doubling one. And so let's compare the two. Okay, so before we had 2 because of the doubling time. We could have had 3 if it were tripling time. Okay, let's write that down. So can also use 3. For tripling time, like if you know the time it takes to triple. And so before, you could actually use any base, whether it's 2, okay, so this is before. This is that old formula, okay? So if you know the doubling time, or the tripling time, or the quadrupling time, okay, you could use that other one. Here, we're using E for the base. Because this one here gives a model relative to the growth rate R. The growth rate R. And we call this one the instantaneous growth rate. Okay, the rate at which it's growing at that particular instant. Okay. All right, so let's take a look at an example of that uses this. All right, so predicting population size. Okay, so let's suppose that the initial bacterium count in a culture is 500. Okay, a biologist later makes a sample count of bacteria and finds the relative growth rate is 40% per hour. Okay, so the relative growth rate is 40% per hour. Okay, so part A, let's find a function that models this. Okay, so we need to use the one that's above. I'll write it down here. N of t equals your initial amount times e to the RT. Okay, so this is the one we want to try to use to write a function, a model for this. Okay, all right, which means we need to have the initial amount and we need to have the rate, the growth rate, the instantaneous growth rate, the relative growth rate. Okay, so we do have that. Let's see. Initial count is 500. So 500 will go right there. The relative growth rate is 40%. So 0.4 times t. Okay, so here is your function. Okay, so we have a function. So in order for us to write this function, we need the initial amount and the relative growth rate, which we have. We have both of those. Okay. All right, part B, what is the estimated count? What is the estimated count after 10 hours? Okay, so now we're going to use this function And we're going to go ahead and evaluate it for t equals 10. 0.4 times 10. Okay, punching that into your calculator, you should get 27,300. Wow. That is growing pretty rapidly. Okay, and here, making a prediction, when will the count reach 80,000? When will, so this one was our answer there, when will the count reach 80,000? All right, so final amount we want to know is 80,000, and we want to know how long that's going to take. So we are solving for t. I'm going to use ln. Here, let's divide both sides by 500. Okay, let's get the exponential by itself. So let's divide this side by 500 and this side by 500. Okay, so 80,000 over 500 equals e to the 0.4t. 80,000 divided by 500 is 160. Again, you can just use your calculator this whole time. I don't have it handy. Okay, solving an exponential, we take the log of both sides. I notice this is e, so I'm going to go with ln, natural log, instead of common log. Okay, and that will allow me to, it's like these guys cancel, so I get 0.4t. I'm going to divide both sides by 0.4. Now I'll go ahead and punch that into the calculator. And I get 12.68 equals t. So that's how long it'll take to reach 80,000. Wow. Okay, so that is it. Hopefully you understand when to use this function model as opposed to the other one. Okay, so this one is when you're dealing with relative growth rate. Okay. The other one is when you know how long it takes for it to double or triple, things like that. This one, it's like, okay, maybe you're not going to wait that long for it to, because it could take a long time for it to double, right? You don't know, and so, but you want to start making predictions right away. Well, then you can just start. You can just collect some data, see that, oh, okay, well, I started with this much, and then it grew by 40%, and then you can use that function to do your modeling. Okay, if you have any questions, make sure you email me or text me, and make sure you are keeping up with the homework. I'll see you next time.